Okay, so we're back. I just wanted to, in my last video, we derived using Maxwell equation we came up with wave equation. I just want to make a small comparison. I think it's going to be a small video. So we're going to make a comparison between wave equation for free space, and then in electromagnetic we have something called transmission line equations, which is normally people drive them. We'll make another video on it. How do we come up with these transmission line equations? So let's just make a small brief comparison. How similar are they? If you were to look at it on this side of the equation, we have del squared, and we already seen what del squared does. Del squared right here. What does del squared do? Del squared is actually a second derivative. So del squared is nothing but a second derivative of that vector, isn't it? So we're just taking a second derivative of that respect to change. Now we'll make a comparison one by one. So we're doing exactly the same thing on wave equation. Now when I look at my transmission line equation, this is also a partial derivative, a second derivative, just like this. And we're also doing it for the electric component. An electric component is actually in transmission line equation is actually voltages, isn't it? Exactly the same thing. Now if you were to look at this, we'll talk about a gamma. In wave equation we also have gamma squared. In transmission line equation we also have gamma squared. We have electric field, we have voltage, which is the representation of electric field. Everything equals to 0. So they are quite similar equation. Now if you were to look at the second equation, wave equation for magnetic field, that is del squared, which is exactly the same thing as taking a derivative, second derivative, partial derivative. I'm just going to use derivative loosely. All right, so second derivative of this, exactly the second derivative of this. Now here we're using magnetic field, and I know what contributes to magnetic field is actually your current, isn't it? Now we also have gamma here, we also have gamma here, we also have a magnetic component, we also have current, which is actually giving rise to magnetic component. So they are exactly the same thing. Here we're talking about in terms of free space, that these waves are propagating in free space. Here we're talking about these waves, or these electromagnetic waves, are going to a transmission line. So they are exactly the same thing. The representation changes a little bit, which is with respect to voltage and current, here with respect to electric field and magnetic field. Let's look at gamma. When we drive this equation, we also know what gamma is. So let me move this paper up. So we also know what gamma is. Gamma in transmission line equation, and specifically gamma, is actually R plus J omega L multiplied by G plus J omega C. This is what gamma is. I'll make a video on it, but just take my words for it. So transmission line equation. Okay, so gamma is complex propagation constant, which means it consists of some real component, and at the same time it consists of something called imaginary components. Imaginary components in transmission line model was L and C, and we have resistance, which is coming from the resistance, the material itself. Then we have something called conductances. So this is some type of a factor, which is, if it's a free if the transmission line is lossless, we know this R and R is going to be 0. When R is 0, conductance is going to be infinity, which means electron can roam around however they want in a transmission line. Now what are the contributing factor here? If you were to look at it, what is my gamma squared? Gamma squared consists of what was gamma squared? Gamma squared consists of omega mu minus omega times E and C. These are exactly the same thing, guys. We have omega, which is omega with respect to frequency, we're looking at it. Okay, and minus 1 is just J squared omega. Then we have mu. What is mu? Mu is permeability of a material. This is a magnetic property. And where does in transmission line the magnetic property is coming from? This is coming from that L, which is that inductor in a transmission line model. That transmission line inductor can be represented in a wave equation in terms of mu, the permeability of a material. All right. Now this, if you were to look at it, I'm just going to forget about that complex permittivity. I'm just going to think of it as a permittivity itself. What contributes in a circuit as permittivity? I mean, what is permittivity? Permittivity is a component which is with respect to electric field. And here in transmission line equation, this is with respect to capacitance. So both of these are equations exactly the same thing. Here they are talking about with respect to transmission line. Here is talking about with respect to fields, is with respect to free space. So I hope you like that small comparison. If you have any question, so this was gamma squared. All right. So if you have any question, just leave it in a comment section. Don't forget to subscribe to my channel. So I'll see you guys later.